That's all right. Okay, so just a quick recap. These numbers could be positive or negative. If they're positives, then of course we're talking about stretching if the value is greater than 1. Like I said, if you see something that is a decimal or a fraction between 0 and 1, your graph is going to shrink. Now, if those numbers have a negative sign also in front of them, that means you will have the stretching or the shrinking depending on the value. But then the negative tells you you will also have reflection, which means your graph will be reflected in the x-axis, right? The h value tells you your horizontal translation. So that means if the h value itself is positive, you should move to the right. If the h value is negative, you move to the left. But you are going with the opposite sign. So when it says x minus 3, that means 3 itself is a positive number, move to the right. If it says x plus 3, that means 3 is a negative number and you're moving left. So only for the h value, the horizontal translation, you have to go with the opposite sign. K is straightforward. If the number k is positive, your graph moves up. If the number k is negative, your graph moves down. Okay, so let's see, we're going to break this up into pieces. So we're just starting with the vertical translation for now. So, like I said, k is positive, graph moves up. K is negative, your graph moves downward. So what we are doing is looking at the base graph itself and then looking at the transformation. So you can see we're just starting out with f of x equals x as our function here. And then the translation is x plus 3, right? So, since we're just using f of x equals x, let's do this one for the x function. So this is b for our f of x. So we're saying basically y equals x. So whatever are the x values can be your y values, right? Because we're saying y equals x. So they will be the exact same numbers for the x function. So that means we'll use this table for y equals x plus 3 here. And you can actually use those same 5 x values if you like. So if we keep the same x values, what will these y values be for the g of x function, x plus 3? Sorry? 1, 2, 3, 4, 5. Yeah? Okay, very good. So what will that graph end up looking like? So go ahead, graph those 2 functions and let's see what you guys come up with. Since we are graphing both of these graphs on the same line, make sure you label both your graphs. Additionally, if you do have colors on you, it may be visually better to see if you can do those in separate colors. If you don't have colors, then just make sure you're at least labeling your graphs. For our first function, we had 0, 0, 1, 1, 2, 2, and then -1, -1, -2, -. That would be our f of x function, right? Y equals x. For the second one, we have 1, 2, 3, 4, and 5. I really cannot draw straight lines, can I? I can't. Obviously, they should be parallel lines, by the way. If you draw good graphs, make sure they look parallel and not whatever this is. Okay, so remember the idea is we're talking about vertical translation, right? So by taking our x function and adding the 3 units, so since we're adding 3, that means our graph should move up. So if you take this point 0, 0 and use that, you can see, of course, 1, 2, and 3, our graph moved up by 3 units. With straight lines, there's not much that you can tell in terms of movement, but if you use a single point, you should be able to, and let me just very quickly show this to you on our graphic calculator. The first function was x, the second one was x plus 3. So again, that's the same idea. This is kind of what our lines should look like, and then using our point origin 0, 0, we should be able to go up 1, 2, 3. So, and you know, obviously that happens with all the points along that line. Each one of them gets moved up by 3 units. Okay. So that would be our vertical translation going upward. Now let's look at our next example here. You can see we're using -3 on a square function. So we should be able to use the same x and y values. What will our first table be? And this will of course be for the x squared function. And this one can be for the x squared minus 3. What are those table values for the first function?
4, 1, 0, 1, 4.
Okay, can I use the same x values here? Yeah, we should be able to, right? Okay, now what will these guys be? Yes, Amy.
1, -2, -3, -2, and 1.
Okay. Yeah, so honestly, to make your life easier, you can take these, because these values here for the y are all x squares, and then you're subtracting 3 from it. So you've got 4 minus 3, which is your 1, 1 minus 3, -2, and that should be able to give us our points here. So you've got 1, -2, -3, -2, and 1. Let's go ahead and graph that. So our base function is 0, 0, 1, 1, 2, 4, -1, 1, and then -2, 4. Since we're not using function definitions here, just make sure you're writing y equals x squared to label your function in this case. Then we had 0, -3, 1, -2, -1, -2. And we had 2, 1, -2, and 1. So, bless you. So again, if you use the origin as your point, you should be able to see that when we count 1, 2, 3, our graph did move 3 units down. So it's that -3. which is making our graph go down, right? So that's actually telling me our k value is -3. Just like in the previous example, it was this +3, the +3, which was making our graph go up, because here our k value was +3. In this case, k value is -3. So like I was telling you before, k is straightforward. Plus, go up, minus goes down. Let's look at our drafting calculator example. This guy will be x squared. This will be x squared minus 3. So remember, these are rigid transformations because the shape of your graph is not changing. You're literally just picking your graph and moving it 3 units down. In this case, for the previous example, our graph had moved 3 units up, which I guess in a line, it would be a little bit harder to tell if your shape was changing or not. In this case, your shape would change in terms of the slope would change on a straight line. But obviously with a parabola, you would be able to tell if your graph had shrunk or it had been stretched. So this is a rigid transformation. You're just picking your graph from 0, 0 and moving it 3 units down to 0, -3. Any questions on these first two examples with the vertical translation?
What would be some numbers that you couldn't put in for x?
Well, remember when we talked about domain and range last time? So it would be if your domain had any restrictions, then those would be the numbers you wouldn't be able to use. But obviously in the straight line example that we saw here with our first example, that's going to be all real numbers for your domain. So you can use anything and it's going to work. And parabola also, x square function has negative to positive infinity as your domain. So in this case, you can actually use any x value for both functions and it would work. So remember, your restrictions would happen when we start looking at the square root functions. That's when our domain is restricted. So then you would have some x values that you wouldn't be able to use. Okay. Okay, so this was vertical. Now let's get into horizontal. So this is our graph moving left and right. Now remember, since our function is defined as x minus h, you go with opposite signs. So over here, we're seeing x minus 3. That means 3 itself is a positive number. So let's see what happens when we graph these functions and what does our graph end up looking like. So we're still using the x square function, which means you can use the same values that we did in the previous example. And then this table can be for the x minus 3 squared. Did I use the same x values?
Yeah, but it's no, you shouldn't.
You need more points than what these values will give you. So we'll start with this, but remember, we'll need to add a few more. And you'll see why when we come up with these numbers. So with this example, parentheses x minus 3 and then the square on the outside, what do these y values end up looking like? So you're going to do -2 minus 3, get the answer, and then square it, right? So what's -2 minus 3?
-5.
-5. And what is -5 squared? 25. So for 1, we won't be able to graph that, right? Because we're just looking at a 10 by 10 grid. What's -1 minus 3? It'd be -4 and -4 squared. 16. Yeah, so he also cannot be graphed. 0 minus 3?
-3.
And -3 squared?
9.
9. So this guy will be fine. 1 minus 3? -2, and of course -2 squared is going to be 4, and 2 minus 3. Okay, so will these be enough points? Do we need more? Okay, so what should we do? 3, 4, 5, and 6. Okay, so let's bring in 3, 4, 5, and 6. So what will their corresponding y values be? 0, 1, 4, 9. Because 3 minus 3 is 0. 0 squared is 0. 4 minus 3 is 1. 1 squared is 1. 5 minus 3 is 2. 2 squared is 4. And of course, 6 minus 3 is 3. 3 squared is 9. Okay. So go ahead, graph that. And let's see what we come up with. So for our base graph, that was a parabola. Okay, so I didn't do a 10 by 10 grid. You guys should be able to do the points with the 9 on them. So even without thinking about if our H value was positive or negative, where are we seeing the movement of our graph happen? It is going to the right. So this is kind of what I was talking about. So here, the H value itself is actually positive 3. And since it's positive 3, that's the reason why our graph moves to the right. So whenever you see a minus sign with that X, that means the number itself is positive. The graph is going to move to the right. So again, if you use the origin, the point 0, 0, you will notice that that point has now moved 3 units to the right. You can try it with this point over here, which was negative 1, positive 1, and you can see this point has moved 1, 2, 3 units to the right. So obviously all the points on the base graph are now moving 3 units to the right. Now let me ask you something before we move on to the next example. What kind of domain and range will both the functions have? So the original f of x function and the g of x function, which moved 3 units up. So what will be the domain for f of x equals x? Yeah, because obviously this arm of our function, the red graph, is going to go to the left to negative infinity. The right arm will go to positive infinity. So it's all real numbers. Very good. What about the range? It's going to be the same. Yeah, same logic, because again, the right-hand side of our arm is also heading up. The left-hand side is heading down. So it's going to cover both x and y axes. What about the g of x function, x plus 3? It's going to be the same thing, right? Because we just moved our graph 3 units up, but it's still going to cover the whole entire space. So in this case, the vertical movement did not change your domain and range for the graph. Now, what can we say about these two functions here? For y equals x squared and for y equals x squared minus 3. And we talked about the x squared function in 2.2. So what kind of domain does the x squared function have? Rexy? What's wrong? Come on. Amy?
It's negative infinity and positive infinity.
Yeah, it's again going to be all real numbers because remember, as these graphs are going up, they're also getting wider, which means they're going to cover all of the x values. So it is all real numbers. Now, what was the range? Sorry, not domain. The range for y equals x squared. What y values will our function have?
Bracketed 0 to infinity.
Yeah, very good. So obviously that's a red graph again. So you know this is going to be starting at 0 and both arms are going up, which means you're only using the positive values on your y-axis. So including 0, bracket on 0, and going to positive infinity. Now obviously we can see we moved this graph down by 3 units. Did that change our domain? No, because these two arms for the green function are still going to get wide as they go up. So you are still using all real numbers on your domain. Did it change our range? Yeah, how?
Now it's going to be bracket -3 to infinity.
Yeah, so in this case, your range will actually change because we did drop that graph by 3 units down. So now it's starting at -3 and going up to positive infinity. So the range will change for this example. And you know, obviously in the same sense, if this graph had moved up, then if we were, let's say, at +3, then your range would have started at that +3. So vertical movement in this case for parabola definitely makes a difference, but then we saw a vertical movement with a straight line really didn't affect it much. So depending on the type of graph, your vertical movement can change your values here. And this example, what is happening with our domain and range here? Of course, this is the same y equals x squared function from the previous example, the same domain and range values. But what happens with y equals x minus 3 squared? Will the domain change because we moved it 3 units to the right? No? No, because yes, we did move our function 3 units to the right, but this left arm is still going to go towards negative infinity on this side, and this right arm is still going to go towards positive infinity. So the horizontal movement for this function does not bother the domain. You're still going to go from negative to positive infinity. Did the range change like it did for the other function? Yeah, because we moved it horizontally, right? So our function is still actually at 0 because this is still the number 0 on the y-axis, right? So you're still starting at 0 and your graph is still going up. So your range in this example does not change. So you can see this is very, very personal, right? The domain and range for each function, it's going to be different. So we cannot generalize and say, for all functions, it's going to do this. No, each individual function will be affected differently. All right, so that was example 3. Did you guys have any questions on that one? Okay, so continuing with our horizontal movement. So James, to come back to your question, this one you will see we cannot use all x values since this is a square root function. So what x values am I allowed in the original square root of x function? I heard 0. Can I go any lower than 0? No, because anything less than 0 is going to start giving me imaginary numbers. So I can start at 0 Now, obviously, you can use anything higher than 0 because they'll all give you positives. But to stay with whole numbers, what can I use for my x values here? 1,
4,
4,
9, and 16.
sure. And what will the y values be then?
1, 2, 3, 0, 1, 2.
Because square root of 1 is 1, square root of 0 is 0, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. Alrighty. For our y equals square root of x plus 9, what x values can I use? So again, remember, we cannot have negatives in there because we're still working with the square root. But does that mean I cannot use negative x values at all? I can? You sure? No?
Yeah. Can't you use
I don't know,
negative,
Trey. I think you're in the minority here.
negative 9 plus 9 would give you 0?
Yeah.
Okay, we're on the second one, sorry.
Right? So the idea is the answer cannot be negative, but some negative x values are going to be okay. So I can use negative 9 because like you said, negative 9 plus 9 is going to be 0. Square root of 0 is 0. But we cannot go beyond negative 9, can we? Can I do negative 10? No, because that's when I start seeing negative numbers for sure. What's the next one that I can use, which is a good number to use?
Negative 8.
Yeah, you can use negative 8, which will give you a y value of 1. Yeah, because remember, negative 8 plus 9 is 1. Square root of 1 is going to be 1. So that's a good number to use.
Negative 5.
Yeah, negative 5 will give you negative 5 plus 9 is 4. Square root of 4 is also 2. Okay, 0. 0 plus 9 is 9. Square root of 9 is 3. And if you wanted to do one more. 7? 7 plus 9 is what? Yeah, 16. Square root of 16 is 4. Now, on the square root of x, you won't really be able to use the 16 and 4 ordered pair, right? Because we are again looking at a 10 by 10 grid. But those first 4 values should be able to get you a decent graph. So this is going to be number 4. Negative 8, 1, negative 5, 2, 0, 3. And what was that last one? 7, 4. so looking at the base graph of square root of x and the square root of x plus 9, what movement did our graph make? You went to the left, right? Because the red is my original graph, and you can see it moved 9 units to the left. So remember, that's coming from this plus 9 because that's telling me h itself is -9. Remember, you go with the opposite direction, and that's why our graph is moving to the left. Because if I had to rewrite that square root of x plus 9 to show you the signs, you can actually rewrite this as x minus -9, and it's those two negatives, which is creating it to be positive. So that's why your graph is moving to the left. So just like we did domain and range for the other functions, what will our domain and range be for both of these guys here? So for the original base function, square root of x, what's our domain?
0 to infinity.
And are we including 0?
Yes.
Yes, we are. Very good. So because obviously we know we cannot use negative x values, which will make our function into imaginary numbers. So you start at 0 and you're only going towards positive infinity. What about the range for that original function? Same, yeah, because again, we are starting at 0 and our graph is only going to go up. So same as the domain. Okay, that's the base function. Now, did anything change when my graph moved to the left?
Yes.
What changed?
The domain.
Okay, and what is it going to be?
-9 to infinity.
Yeah, so just like we were looking at the table, we had to start at -9. So you will notice my domain, is going from -9 to positive infinity, and again, including -9. Did the range change?
No.
No, because even though my graph moved left, I didn't move up or down. So I'm still starting at 0, and my graph is still only going up. So the range will stay the same as the original function. The domain is the only thing that changed when I moved my graph to the left. Any questions on number 4? Okay, so this was our horizontal translation, moving our graph to the right or left. So remember, this is where we go with the opposite sign for the h value. Now let's get into reflection. So remember, as I was telling you, when we are looking at reflection, the reflection happens when we put a negative in front of our function, or if that a has a negative sign. So here, you can see we have the original function is y equals x, and we're putting a negative in front of the x, so that's what's creating the reflection, is that negative sign in front of the original function. So we're talking about, we get a graph that is a mirror image, and in this case, your mirror would be placed on the x-axis, so it's going to reflect on the x-axis. They're saying we simply change the sign of the y coordinates to get that reflection. So again, we're looking at our basic y equals x function, which is what we did in example 1. So you can use, again, those 5 standard x values, -2, -1, 0, 1, and 2. This is for the original y equals x function, which means, of course, these points will be the same. Now, if I use the same x values here, and this is now the function y equals -x, how are your y values going to change from the x function to the -x function?
Just the sign.
Switch the signs, because technically I am taking negative of the x value, and my x value happens to be a negative number also, right? So the two negatives will make it into a positive which will make this into a positive also. 0, of course, takes no sign. Now, when my x values are positive themselves, and I put a negative in front of it, that'll make a positive into a negative, right? So your signs literally change from the original function to the reflection. You're just basically switching your signs around. So when we graph this, what will it end up looking like? Whoa. So we've got -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. This will be our original function. That's the y equals x, right? Now, with the negative x function, we still had 0, 0, but then our signs had changed. So for -1, it was +1, -2 was +2, +1 is -1, and +2 is negative. Right? Y equals -x. So remember what we said, your mirror is placed on the x-axis. So imagine if you have that mirror right here, then this upper red arm here is the one that's getting reflected down here, right? So that's the reflection. And then on this side, this is my original function again, which is now getting reflected on the top half. So your reflection is happening, this guy is going down here, and this guy is coming up here. So that's how this reflection happens, always with respect to the x-axis. So the negative is what is creating the reflection. Okay. Again, to have our discussion for domain and range. What will, with the original x function, what will the domain and range be? That's the red. For
Domain.
domain? Yeah, very good. And the range?
Same thing.
It will be the same thing because we already talked about this function in example 1. Okay. How does the reflection change that domain and range? It doesn't, because even though the reflection happened on this green graph, this arm is still going to go towards positive infinity, this arm is still going to go towards negative infinity on the x-axis. And then of course, since this arm is going down, he's going towards negative infinity on the y-axis, and this arm will be going up to positive on the y again. So for both functions, domain and range are the same intervals, negative to positive infinity. So you can see reflection didn't change much when it's a straight line, but change that to a different function and you may get a different result for domain and range. So very specific to each function. Let's take a look at one more example with reflection, and instead of using a straight line, we're back to using our square root. All right, let me see what you guys can come up with for this one. You should be able to use these examples we've looked at, and let's see what those reflections look like. Okay, so again, most of you guys have this down already. You can definitely use the same x values, but the only difference is from the y equals square root of x function to negative square root of x, all of these values will now become negatives, right? And so graph will look like 0, 0, 1, 1, 4, 2, 9, and 3, somewhere over there. And then remember, we're talking about reflection in terms of the x-axis. So again, obviously our starting point is the same, but now you're looking at 1, negative 1, 4, negative 2, and 9, negative 3, somewhere over there. So Amy, your first clue should have been it's not a reflection with the x-axis, right? So that would have told us whether we did the graph correctly or not. Okay, so most of you had this, but some of you were still working on your domain and range as I was walking by. So for our first function, and we looked at this in the previous example, so you should have that information. We're going from 0 to infinity on the x, 0 to infinity on the y. But when we did the reflection, what happens with the negative square root of x? Does your domain change? No, because even though we created a reflection in terms of the x-axis, we're still starting at 0, we're still going to the right, we're still going to positive infinity, so your domain does not change. Will the range change?
Yes.
Yes? Because what happened here? When you created the reflection, our y values are no longer positive, right? You saw in the table, all our y values became negative. Even if you look at the graph here, you can see our graph is going to start at 0, but obviously it is now heading downwards, which means it's going towards negative infinity. Now, when you write your intervals, remember we write the smaller number first, which means technically, I guess we are coming from negative infinity and we're going to stop at 0. So that's how you would write your range for this second function. So in the previous example, since we were using straight lines, that reflection did not change our domain and range. They stayed the same for both functions. But now here, because we changed the function, we're using a square root, we notice that our range will definitely change from the original function. So like I said, it's very specific to the graph you use, to the function you use when you're working with these examples. So we've looked at vertical translation, horizontal translation, and reflection. Remember, all three of these transformations are rigid, right? They do not change the shape of our graph. They just move our graph left and right, up and down, or maybe we're reflecting them on the x-axis. Now, we'll get into the non-rigid transformations, which is where the actual shape of your graph will change. Just before we get to the stretching and shrinking part, let's go ahead and look at this paragraph right here at the top. So we're saying when the function y equals x squared is reflected in the x-axis, and then, so we're talking about reflecting it, and then translating it 1 unit upward, the equation of your final graph, or the final position, comes out to be y equals negative x squared plus 1. But if I change that order, right, instead of reflecting first and then moving it up, what if I moved it up first and then did the reflection? So if I reverse that order, you will notice how our function changes, because I'm moving it up first and then I'm reflecting it. So you will, if I'm, again, you distribute that negative sign, you actually end up getting negative x squared minus 1. This guy here was negative x squared plus 1. So in what order you do your transformation will actually make a difference into what your final graph is going to look like. So we're saying in the order in which the transformations are done can make a difference, but we actually use a rule where we say, let's do this transformation first, then this, kind of like we do with, please excuse my dear Aunt Sally, right, when we do order of operations. So that way everybody gets the same result, because let's see what these two graphs are actually going to end up looking like. So I've got negative x squared plus 1. So you know what, let's leave him as our base function. We are doing negative x squared plus 1. So remember the order in which we did the translation. We talked about let's reflect it first, then move it 1 unit upward. So when you did the reflection first, we took this red graph and we just inverted it. That's why we saw the first position of the graph right over there. And then we moved it 1 unit up, which means then from 0, 0, you're moving it 1 unit up. If we did this in 2 different positions, let's say I take this guy, I'm doing the reflection first, then I'm moving it 1 unit up, right? So that's the way this graph moved. Now for that second one, we were talking about translating it upwards by 1 unit first and then doing a reflection. So what does this guy end up looking like? So again, keeping the red graph as our base, let's start by moving it upwards. So that's the black graph. We took the red graph and we moved it 1 unit upward. Now, let's reflect this guy. So if I'm reflecting this guy, I'm actually going to put a negative in front of it. And can it give me color choice here? Nope. Don't want to really use the red, but I guess we'll go with it. So that's happening with our original x squared function being moved up to 1 unit and then reflecting it down. So look at the difference between this second red function and the purple. Those are what those two functions are giving us. You're not going to end up with the same graph because based on the order that you did this transformation, you get completely 2 different graphs with 2 different definitions, 2 different functions for them. So you have to be very careful. So again, let's get rid of this guy here. Let's get rid of the original function, and that's what those 2 final results end up looking like. Okay? So that's why order of these functions is very, very crucial, and we'll be talking about that once we're done with these stretching and shrinking examples. Okay. So remember, when your a value that's right in the front of your function, if that value is going to be greater than 1, that's when our function stretches. If the value of our a is going to be between 0 and 1, then our function, our graph, is going to shrink. And it's actually easier to see how stretching and shrinking works with a parabola as opposed to a straight line, but I'll show you an example with a straight line also. So let's go ahead and do our tables for these 2 functions, and then actually 3 functions, and then let's see what those graphs will look like. So of course, for our y equals x squared function, we can use our standard 5 points. We'll do the 1/4 x squared here, 1/4 x squared here. So what should those x and y values look like? Can I use the same x values? Yeah? Okay, let's try what happens. So what do my y values look like for the 1/4 x squared function? Lexi?
So it's gonna be 1 and then 0.25 and 0 and 0.25.
What was this guy?
What could be fine?
For number 1?
Yeah.
This guy was, again, use the base function to help you out. I already have my x squared values and I'm multiplying it by 1/4. Basically, I'm taking a quarter of those numbers, right? So 4 divided by 4 gives me 1. 1 divided by 4 is 1/4 or 0.25. 0 divided by 4 is 0. Again, 1 divided by 4 is 1/4 or 0.25. And 4 divided by 4 is going to give you 1. If those, you have 3 good ordered pairs here, these guys here in the middle and the ends, but if you need more, then calculate more points. Now what will happen with the 4x squared? What did those x values end up, y values end up looking like?
164046.
Yeah, same thing. I already have my x squared values from the original function. I'm just multiplying x squared with 4. So take all of these y values from the first table and multiply each one of them by 4. So you will have 4 times 4, which is 16. 1 times 4 is 4. 0 times 4 is 0. 1 times 4 is 4. 4 times 4 is 16. And again, we've got 3 good points right here in the center that you can use to graph. I'm not sure what other x values you could use and get good numbers because you'd have to go into fractions then. Okay, so let's see what this graph ends up looking like. Okay, so our base function is just the x squared. So we're trying to see how the stretching and shrinking will happen. So with the 1/4 x squared, we had -2, 1, 0, 0, and 2, 1. -2, 1, 0, 0, and 2, 1. Actually, I think I can use 4 and 4, or -4 and 4, and this guy's. So did it stretch my graph or did it shrink my graph? Stretch? Shrink?
It stretched it.
Kept it the same?
Oh, the 1/4. Just stretched it.
When the value is between 0 and 1, it shrinks it, or in other words, makes it wider. Because again, the 1/4, if A is between 0 and 1, your graph shrinks or basically becomes wider. Okay, it kind of flattens out, right? Because that's what it's doing. Okay, let's see, with the 4x squared, what did we have? Oh, -1/4, 0, 0, 1, 4. So let's see, -1, 4, 0, 0, 1, and 4. So think about, imagine what happens to a rubber band when you stretch it, right? It becomes narrower. So that's kind of what's happening with that 4x squared function. Again, in the red is our original function, and you'll see with the 4x squared, it became narrower. So in values where a is greater than 1, your graph stretches, or basically it becomes narrower. Okay, and again, just to show you what this would look like on our graphic calculator. Let's start with our x squared function. We're doing wrong place. One-fourth x squared, and then of course our 4x squared. Okay. So it's hard to see, but you have the purple, which is the original function. You have the blue, which is the shrinking, and the green is the stretching. Okay. Okay, let's see. We talked about the domain and range here, so let's talk about the domain and range for these functions. What changes? So that's the original function x squared going from negative to positive infinity for both domain and range. One-fourth x squared. What will our domain and range be? Did my domain change? No, because I shrunk my graph for the 1/4 x squared, but obviously my arms are still going to head towards positive and negative infinity, so they haven't really changed. And I just realized what I did.
I just about to ask, I said, wait a second, I hit some.
Yeah. It's like, what new function are we talking about? What's the range for 1/4 x squared? Did that move up or down? Yeah, our graph did not move up or down because we're still going from 0 to positive infinity on our y values, so that hasn't changed. For 4x squared, is that the same? Or does it change? No, you're just going faster because you're multiplying by 4. You're going to get to your y values a lot quicker than the other two functions. Okay. So that's your stretching and shrinking using the square function. Now what will happen if instead of using x squared as our base function, if we went back to using y equals x as our base function, and then we tried stretching and shrinking on that? So that's our base function, just a straight line, slope of 1, passing through the origin, right? Y equals x. What will happen, just keeping those same numbers, if I used 1/4 x? How is that going to shrink our graph? The slope will change. So should it become steeper than the base function or less steep? Less steep or steeper? Steeper? Less steep? Less steep? Less steep? Okay, let's see. We are doing 1/4 on the x. less steep, right? Because you are decreasing the slope. The slope was 1 on that original function, but now you're making it 1/4. You are making the function less steeper. So obviously that means if I were to multiply by 4, it would be more steeper. Man, try riding a bicycle on that 4x slope. You'll never see me again.
That's what Susie was doing.
That was Susie was doing, coming down. Okay. Alrighty. So you can notice that how different this looks from an x squared function, right? With the parabola, we were kind of able to see, okay, it got flatter, right? It got wider with the shrink, but then with the stretch, of course, it gets closer. And like I was talking about, think of that rubber band, what happens when you stretch it. That's kind of what happens with that x squared function. Here, with the straight line, your slopes will change, right? So your slope's going to get either much more steeper, like it did with the 4x, or maybe get a little bit less steeper with the 1/4. Okay, so now that we have looked at each type of transformation, let's go back and talk about this next part here. So they're actually comparing the ordered pairs from our tables here, and you can kind of see how that is also affected in our ordered pairs. Your numbers change, right? You can see how large my y values are in the 4x squared function, and for those same x values, your y values are going to be much smaller on the shrinking function, because obviously that's making our function go a little narrow, wider, get flatter. Okay, so when you put all these transformations together in one function, how do we go about doing that so we don't run into the issue of you having one equation but you having another one, right? So we want to keep an order to our transformations, and this is what your order looks like when you are doing multiple transformations. We always start with the horizontal translation. This you can do in any order, but that's got to be the next step. So start with the horizontal translation, then you can do reflection, you can do your stretching or shrinking, whichever happens. In the same function, your graph will either stretch or shrink. You cannot do both of them in the same graph, right? So reflection, if you see a negative sign, and then based on is that value of a in front of your function greater than 1, you will have a stretching effect. If the value is between 0 and 1, it's going to shrink. The very last transformation that we do is the vertical translation. So that's coming from our k value, a value with the stretching, shrinking, and of course if it's negative, it's a reflection, and the h value gives us our horizontal translation. So identify your a, h, and k values in this function first. What is, let's start with the h since we do the horizontal translation first.
-6.
-6?
Oh wait, no, that's not underneath that. -2.
-2, yeah, because your h value is actually coming from right here. So we have an h of -2. Remember what we said, go with the opposite sign, which means our graph, since it's negative, our graph ends up going to the left. What's the a value here?
-1/2.
Yeah, so the a has both a negative and a 1/2. The negative actually tells us there will be a reflection. And what does the 1/2 tell us? It's going to shrink. Yeah, very good. So that's a shrink. So we have reflection, we have shrink, we have horizontal movement to the left. What else? What's the k value here? +4, yeah. So if k is +4, what direction does our graph move in? Yeah, it will go up. Okay, so the reason why I have so many tables is you have to start out with what the base function is. So in all of this, like we saw in our previous examples, my base function was x squared here. My base function was a square root here. This was the straight line y equals x. This guy was square root of x. This guy was x squared. So in this example, what's your base function?
So
Yeah, square root of x is the base function. So this guy actually is for the initial table for square root of x. Then they want us to do the horizontal transformation as the first order. So that means we are doing the -2h part. So that's going to come from square root of x plus 2, and hopefully you can write it a little bit better on your paper than I can on the screen. But you're going to then do the square root of x plus 2 part next. And I'm actually breaking the reflection and the shrinking in 2 parts, so it's up to you what you want to do next, but I guess I'm going to do the reflection, so that's going to be negative on square root of x plus 2. So that will take care of our reflection. Then you can do -1/2 square root of x plus 2. So that will be reflection with the shrinking. So base function, square root of x, then the horizontal movement, square root of x plus 2, then the reflection, so just putting a negative in front of the square root of x plus 2. Then we're doing the shrinking, so that's -1/2 square root of x plus 2, and of course this last one will be for the entire. So this will be -1/2 square root of x plus 2, and then our vertical comes at the very end, so that's the +4 at the end. And we will be graphing all of these individual movements separately on the same graph. Okay, so we are starting out with our square root of x. Square root of x, which means you can use 0, 1, 4, 9, and 16 as your x values. So our base function how are you going to modify your table for the horizontal movement? For this second one, so this was our square root of x. This is square root of x plus 2.
You can keep the same x bar for x according to where you cross from it.
Can we keep the same x coordinates all the way across?
We can also add -2.
Okay. But will all of these numbers work? Because some of them will actually end up giving you a decimal now. You won't get clean answers for the same. Amy?
I started up doing one -2, -1, 0, 1, and 2, like the normal 5.
Okay, but some of them again will not give you whole numbers, right? It's like 0 is not gonna work. 1 is not going to work.
-2, 2, 7, 14.
You can use -2, you can also use -1. You said 2. So let's see, this gives me a 0, this gives me a 1. This will give me a 4. And you said 7. Yeah, that should work.
14.
14, which we won't really be able to graph that guy. But -2 plus 2 is 0, square root of 0 is 0. -1 plus 2 is 1, square root of 1 is 1. 2 plus 2 is 4, square root of 4 is 2. 7 plus 2, of course, is 9, square root of 9 is 3. And again, just so that we have this, 14 plus 2 is 16, square root of 16 will be 4, right? So that should be starting at -2, 0. So -2, 0, -1, 1. What did we have? 2 and 2? And then 7 and 3. So this will be the y equals square root of x plus 2 function. So remember, this is rigid, which means you just took the square root of x graph and moved it 2 units to the left. That's all that's happening. Everybody okay so far? Got our graph moved 2 units to the left? Okay, so I had done reflection next. So that would be just basically putting a negative in front of this function. We should be able to keep the same x values. What will happen to our y values here?
Negative, right?
Yeah, they're all just going to have a negative in front of them. 0, of course, will stay 0, but these guys will become -1, -2, -3, -4. And that's kind of why I like to do these guys next to each other, so it's just easy for us to make that transformation happen. So let's see, we are doing the reflection next. I'll use the black one here. Let's see, reflection. So I'm still starting at -2, 0, but now I have -1, -1, +2, -2, and then +7, oh boy, -3 somewhere over here, I think. So this will be y equals negative square root of x plus 2. So we've taken care of our reflection. And of course, remember the reflection happens in the x-axis. What was our next transformation?
Moving it up.
Sorry?
Moving it up 4.
Moving it up 4? Why 4?
Actually, no. Sorry, horizontal.
It's going to be the -1/2, right? So the -1/2 square root of x plus 2. If you just take a second to think, what's the change that's going to happen from this table to this table, from the negative square root of x plus 2 to the -1/2 square root of x plus 2? You're actually going to just reduce the y values by half, because that's where our shrinking is happening. So we will actually keep the same x values, because we're not moving our graph horizontally at this point. We're just shrinking it. So you are taking from our third table here, you're taking all of these y values and dividing it by 2, or multiplying by 1/2, however you want to look at it. 0 divided by 2 is 0. -1/2 divided by 2? Negative 1/2 or negative 0.5? Negative 2 divided by 2. Negative 1. Negative 3 divided by 2. As a decimal, what does that guy come out to?
-1.5.
Yeah, negative 1.5. That might make it easier for us to graph. And then negative 4 divided by 2. Negative 2. So you can see once we actually break this down into phases, you don't have to start all the way from let's see what the x values need to be and figure out your y values. You can just make that transformation, go from one to the other. So again, we're starting at negative 2, 0, but everything is now in halves. Negative 2, 0. Okay, I guess I'm going to use a flow this time. Same starting point, but instead of at negative 1 and negative 1, I am going to be literally halfway between the x-axis and this point right here. And it's probably going to get messy for you guys, I'm going to imagine. So if you really have a colored pen, that will really help you out at this point. For positive 2, I was at negative 2, so it's actually going to become positive 2 at negative 1.
Yeah.
And then we had what, 7 at 7 at 1.5. Okay, so that's going to be 1.5. Right. Well, technically that should be halfway between those, and looks like my calibration's gone off a little. Okay, but kind of halfway between the x-axis and this curve that's in the black here on the screen. So something like that. Yeah, my calibration is definitely off. This guy will be y equals negative 1/2 square root of x plus 2. What's the last transformation we are left to do?
Add 4 to those.
Add 4. So how will our last table change? So adding 4 will move our graph vertically, right? Because that was the last translation, which means again, we're not moving horizontally, which means your x values can actually again continue to stay the same. From that 4th table to the last one, how do I change my y values?
Add 4 to those.
To all the y values, you are adding 4 now. So you are literally taking these values from the last to second to last table and adding 4. So 0 plus 4 is 4. Negative 1/2 plus 4?
3.5.
3.5. And it'll be positive 3.5. So 3.5 or 7/2, since I'm keeping them in fractions, I'll leave it as a fraction.
3.
Negative 1 plus 4 is 3. Negative 3/2 or negative 1.5 plus 4? 5/2, which will come out to be,
2.5.
yeah, 2.5. And the last one, negative 2 plus 4.
2.
2. There we go. So we've got some good numbers we can use in there. We're now at negative 2, 4. Okay. I guess I'll use red to do our final example here. Okay. Negative 2 is now moving up 4 units. So remember, this is that last blue graph that I did, which is now moving 4 units up. So that's going to be 1, 2, 3, 4. This guy was at negative 1/2. So he's going to be at 3.5. Where were you at? Negative 1. So he's going to be at 3. Wasn't that? Yeah. 7 is at 5/2. So 7 is at 2.5. somewhere over there. I needed one more color. And this is our final graph, -1/2 square root of x plus 2 plus 4 on the outside. It's not. Okay, so we started out with the square root of x function as our base function. We moved it 2 units to the left when we added that 2 inside the parentheses, right? So that was our second change that happened, or actually, I guess the first change that happened. That's our first transformation. Then we did a reflection to that. Once we reflected it, we shrunk our graph by 1/2. And then the very last thing we did was move it 4 units up. It looks a little less jumbled here than it does on my screen. So first original graph, moved it 2 units to the left, reflected it, shrunk it, and then vertical movement. So your final graph, obviously, if we take all of these guys out, that is what your final graph should end up looking like. But you can see how in phases it changes from the base function to the final result. Okay? Okay, let's actually go back to this here. Our original function will have a domain and range, as we've seen in the past examples, of going from 0 to infinity and 0 to infinity, right, for our domain and range. I'm not going to do for the different transformation phases, but what is your domain and range for this final graph that we did?
Domain is -2 to infinity.
Okay, give me 1 second. So that's the -1/2 square root of x plus 2 and then plus 4. Okay, go ahead, Raylan.
Domain is -2 to infinity.
Okay. Do we agree with that? -2 to infinity? Yeah, because even though all of these other transformations happen, again, that's this red and blue graph, I guess, that I did. You're still only at -2, right? We haven't gone any further out to the left. So we're still starting at -2 and going to positive infinity. Because after our original function, that was the first transformation we made, and all the other transformations still stayed at -2. So yeah, your domain is starting at -2 to infinity, of course, including -2. And what can we say about the range for this final function?
-infinity to 4.
-infinity to 4?
Or negative infinity.
Sorry?
Would be 4 to negative infinity.
4 to, well, no, the order is fine because you do write the smaller number first. Do we agree? Do we want to change that? Okay, so remember, we're talking in terms of the y value. So how far are we going on the y value? So obviously, again, this arm of our function is heading down, right? Because it's a parabola facing downward. So this arm probably a bit slowly, but he's still going to make his way down. So it is definitely going to negative infinity. But then how far up are we going on the y-axis? And this is again the end point of this final graph. So you are only going to -4. There is going to be no graph beyond that, sorry, +4. There is no graph beyond 4. So you will be going, I guess, from negative infinity to 4 and stopping at 4. So what did we notice here in terms of our transformations that affected our domain and range?
The horizontal translation affects the domain and the vertical translation affects the range.
Yeah, so in this specific example, the horizontal transformation dominated our domain change, right? And the vertical translation dominated our range change. Now remember, again, this is very specific to this example. It's not going to be, if we were using a square function, it may not have the same domain and range changes. So it's very function specific, but obviously that's your final answer for the domain and range for this multiple transformation. So the key thing is you need to remember the order of transformation. So always start with the horizontal, then your reflection, stretching, or shrinking happen at the same level, and the final change is always going to be the vertical translation. Now, not all functions will have all 3 levels of transformation, right? Some of them may just be horizontal with the reflection. Some of them may be stretching or shrinking with the vertical. So just kind of look at the function and make your decision. Yes?
I was just gonna ask, on the test, are you gonna want us to do like all the tables and have every coordinate, or just do it step by step?
Okay, that's a great question. So she wants to know on the exam, do you have to do the exact same process that we did here, the different tables and then the different graphs, right?
We have to show our work.
Okay, so no, the short answer. The long answer, in a way, yes. Okay, if that's confusing you, I want you to do the table. I don't want you to do a multiple graph, because you can see it does get messy, right? And especially because on your exam, my math lab will sometimes give us a really nice grid, sometimes it makes it really small. So to avoid any confusion, you draw the final graph, but I want to see the transition of the table happening. So just like we did here, show me the transition on your table, but graph only the final table. Does that help answer your question? Okay. Alrighty, so we'll do the table, but we won't do the multiple graphs. All right, guys, have a wonderful evening. Keep working on your chapter 2 homework. If you have any questions, please let me know. We'll see how far we can go on chapter 2 by Wednesday. And I'm kind of potentially thinking the next week for exam on chapter 2. So kind of keep that in mind as you're working through homework. Okay? All right, have a wonderful evening. I'll see you guys on Wednesday.